what Arjun and I are going to talk about today is the introduction to the new random effects methods in RevMan. And the outline will be that I'm going to first of all talk about the process that we have used to develop the recommendations for the random effects meta-analysis methods. Then I'm going to hand over to RG, who will talk about, recap the random effects model and outline the new random effects methods recommendations for when to use them and why, and how they may impact the results. And we're going to do this via example in the main, not through formula. We're going to talk about the new heterogeneity estimator and confidence interval method, the confidence interval method for the summary mean effect, and also the prediction interval. And I will also talk about some suggestions for what you would write in a protocol, and then hopefully we'll have some time for questions. So before we get going, it would be helpful for us really to have a poll as to which role best describes you. So I think that poll has been shared with you now, so we'll just wait a short amount of time. So we're up to over 80% participated. So I think we can share that poll now. And what we've got here is mostly systematic reviewers. We've got some statisticians and methodologists. So that's great. Hopefully the presentation then is pitched appropriately for you. And my apologies to statisticians who are very keen on seeing formula. All right. So I just want to begin, first of all, by talking about the process that we use to develop and implement the recommendations. So really, this started in earnest, I guess, in 2020, although I should say that we first started talking about these different methods that could be used in RevMan back in 2013 at the Quebec Colloquium. So this has been bubbling along for a very long time. But in 2020, when I say we, really the Cochrane Statistical Methods conveners and some other people who are listed over on the right-hand side there. But we updated some systematic reviews of statistical simulation studies that examine the performance of the heterogeneity estimators and confidence interval methods for the summary effect. And these were reviews that had originally been led by RG. And then we also, with that, examined the impact of adopting the different methods in the Cochrane library. So we applied those methods to thousands of meta-analyses that are in the Cochrane library. We convened multiple meetings over a period of a couple of years to review and discuss the evidence and form the recommendations. And then in January 2022, we submitted those recommendations to the methods executive, and Cochrane endorsed those in September of that year. And there's been some revision to those recommendations this year. And so this is the team that were involved in developing the recommendations. They consist of, as I said, co-conveners of the Cochrane Statistical Methods, leads of the systematic reviews, and of a large simulation study that examined the different methods, heterogeneity estimators, and at the time, the Cochrane Methods Support Unit Lead and Statistical Editor. So that's been the kind of process to develop the recommendations. In terms of implementation, this has really been happening, I think, from about start of 2023, or maybe late 2023. And this is about the integration of the methods into RevMan, and then obviously the kind of translation activities, like updating Chapter 10 of the Cochrane Handbook, webinars such as today, and updating training materials and other workshops. And our link, the people who've really been involved in this are Ingrid Avelo Rodriguez, who's the Cochrane Methods Implementation Editor, Rebecca Hall and Gert van Wolkenhoff from Cochrane IT and RevMan. We've also had specialist statistical advice from Julian Higgins and Wolfgang Wiechbau. RG and myself have kind of been links between all these groups, and also Simon Turner at Monash University has done some of the testing. So with that background, I'm now going to, I should say here that really, while it seems quite a linear process as I've laid it out, it's really not like that. There are kind of things that happen as we go along that make us revisit earlier points. And so there are still some little issues that we might be ironing out. So I will now hand over to Arji, who will start taking the next part of the presentation. Thank you, Archie.
Thank you, Jo. So now we'll start with the random effects model as presented in this slide, where the observed study effects presented as gray boxes estimate different true effects represented by dotted green vertical lines, and these are the unobserved effects. So differences in the observed and true effects are attributed due to random error, as you can see here with the horizontal black lines, and variation in these true effects, the green dotted lines, is attributed due to heterogeneity. Now, we assume that the true effects are related and come from the same normal usually distribution with common mean, the summary effect, which is mu, as depicted here, and variance, the tau square, which is the heterogeneity. So this tau square, the variance, the heterogeneity is the variance of the true study-specific effects, the different dotted lines. Now, the primary interest in meta-analysis is estimating the summary effect, this mu. However, a key strength of meta-analysis is the ability to also assess heterogeneity between the study effects. So focusing only on the summary effect can actually be seriously misleading. So the overall aim is to infer on both the summary effect, the mu, and the dispersion of the studies, the heterogeneity. Now, let us consider this example where we have 4 studies on Guillain-Barré syndrome, the GBS. And as we mentioned, the summary mean effect is of primary interest. So to have the overall picture and possibly be able to generalize our results, we also need to estimate the between study variance and the prediction interval, incorporating the true effect in a future study. And we can also compute several other statistics such as the I-square or the H-square. So in this empirical example, we estimate heterogeneity, as you can see, using different approaches. We have the Dersimon and Laird, we have the restricted maximum likelihood, the Siding-Jonkman, and so on. However, changing a random effects method impacts on the summary confidence interval. And the confidence interval, as you can see, spans from decreasing the odds of having an event by 3.28 on the log odds scale, up to increasing the log odds by 0.50. And also the estimation of tau of the heterogeneity using the particular methods that we see have produced estimates ranging from almost 0 up to 1.58. And this actually impacts on the summary effect and the precision of the summary effect. However, it should be considered that estimation of heterogeneity will also impact on the prediction interval, on the calculation of the prediction interval, and Jo will be introducing this later. Therefore, the choice of the heterogeneity estimation method may give different results and can impact on the summary mean effects and its confidence interval. And similarly, the method to estimate the uncertainty around the mean effect, the summary mean effect, may impact on its interpretation. Now, the Dersimon and Laird has been, up to recently, the most frequent method, random effects meta-analysis method used, and in particular, the wall-type confidence interval based on the normal distribution and the Dersimon and Laird estimator for heterogeneity have both been commonly used and have been the default options in many meta-analytical software, and up until recently, the only random effects method in RevMan. However, these methods may be misleading, particularly in small meta-analysis, and therefore alternative methods have been suggested in the literature, and these alternative methods have potentially better performance in some of the cases. Now, on behalf of the Statistical Methods Group, we published 2 papers in the Research Synthesis Methods Journal based on the literature and including statistical simulations and empirical evaluations. And based on these findings, we provided recommendations for methods to be implemented in RevMan. Now, as already mentioned, today we are going to discuss the process. We are actually in the process of finalizing the update of RevMan, and we're going to discuss about all these recommendations. And previously, it looked like this, RevMan looked like this, as we see on the left-hand side of this slide. But now, what we are going to change in the update of RevMan, instead of having one random effects meta-analysis option, we are going to also add options about heterogeneity, as well as options about the summary effects, the confidence interval around the summary effect. So this is what we are going to discuss in the next few slides. Now, let's see the overall random effects meta-analysis methods to be implemented in RevMan. Overall, we have 5 levels. I'm going to start with the 3, which refer actually to the quantity of heterogeneity. So in number 1 here, we can see we have the tau square. So what we have added actually is the restricted maximum likelihood as a new method, along with the de Simon and Laird. So the restricted maximum likelihood will be the default option, whereas the de Simon and Laird will be the optional option. And as a second step now, and this is new, we have added also the option to calculate confidence intervals for the tau square. And usually this is recommended for meta-analysis that have at least 5 studies. And then as a third step, we have the I-square, which will be calculated according to the method used for estimating the tau in step 1. Of course, interpretation will remain the same. And then, as a fourth step, we have the confidence interval for the summary effect. We are going to discuss the 2 options that we'll have. We'll have the Hartung-Knapp-Sittig-Jonkman method and the wall-type method. And as a fifth step, we have the prediction interval for the summary effect. And this, again, will be optional, and we recommend this when we have at least 5 studies. Overall, formulas for the statisticians potentially will be provided in the RevMan web statistical algorithms. And we also are going to provide a short description of these approaches in the Cochrane handbook. Now let's start with the inference on heterogeneity. Now, for the between study variance, we will be able to select between REML and de Simon and Laird. And as I said, the restricted maximum likelihood method will be the default option. Then we also have the option to calculate a confidence interval for the heterogeneity, the tau square, which is calculated using the Q-profile method. And as a third step, we have the I-square, which will be calculated, as we said, according to the tau square, the estimator that we have chosen between REML and DL. So this will be automatically calculated based on this selection. We won't have to conduct any calculations on this aspect. RevMan will do all these calculations for us. Now, I would like to highlight here that our recommendations are driven by simulation studies with scenarios according to the characteristics from Cochrane reviews. And based on empirical studies on Cochrane reviews, we found that most of the meta-analysis include a small number of studies, fewer than 10 studies. Also, an empirical study using around 60,000 Cochrane meta-analysis has shown that heterogeneity fails to be detected, especially in small meta-analysis. So this heterogeneity is usually higher than what it is assumed. So this suggests that we need alternative methods to estimate heterogeneity. But also, the majority of pairwise meta-analysis include fewer than 10 studies and even fewer than 5 studies. Now, before we make any inference on the choice of other estimation alternatives than the de Simon and Laird, we need to understand which are the main factors that may affect this between study variance estimation. And in particular, exploring scenarios within simulation studies that represent the characteristics of Cochrane reviews. So these factors include, according to the published studies, the published simulation studies, include the number and size of studies, the magnitude of heterogeneity, and frequency of events, among other factors which are usually typical for meta-analysis. So in the next few slides, we will show examples on these factors and how they can affect estimates on heterogeneity variance, and how the meta-analysis results may be impacted by using the new restricted maximum likelihood method. Now, let's start with this first example. This is a Cochrane review on acupuncture for dysmenorrhea. We have 6 studies in total, and the effect size is mean difference. Now, using the popular estimator for heterogeneity, the Dersimone and Laird, we can see that heterogeneity is equal at 1.43. Now, using the newly suggested approach, the restricted maximum likelihood, we can see that the estimated between study variance now is 2.82 approximately, and that's greater than what we previously estimated with the Dersimone and Laird. And of course, this will impact on the confidence interval of the summary effect. And now you can see that this is wider than before. And in some cases, this can include or exclude the null value. Now, overall, simulation studies have shown that in accordance to this example, the Dersimone and Laird underestimates the true heterogeneity and therefore produces very narrow confidence intervals for the summary effect. But simulations have shown that restricted maximum likelihood is less downwardly biased, less biased than the Dersimone and Laird. Also, some people find that tau square is difficult to interpret, particularly because we cannot compare tau square across different meta-analyses and different effect sizes. We don't have universal thresholds for this. So we prefer sometimes to use the Q statistic and the I square on the dispersion of the studies. And here we can see that the heterogeneity estimation impacts on this I square calculation. So we range from 89% now, we move on to 94%. So this is an important increase, I would say. Now, despite estimating the between study variance, this is always an estimate, and estimates are usually imprecise, especially with a small number of studies, such as in this case, where we have only 6 studies. And even if we had thousands of participants, it would be challenging to obtain a reliable, a valid estimate for heterogeneity. So we need a lot of studies in order to adequately estimate heterogeneity. And in this case, an estimate of the amount of heterogeneity can be surrounded actually by a confidence interval. And here I present the 95% confidence interval for tau square, which we can see ranges from 0.82 up to 19. And that's a really wide confidence interval for heterogeneity. So it shows us that potentially this heterogeneity here in this example is high, but also it excludes the value of 0. So overall, the precision of heterogeneity depends mostly on the number of studies. And particularly here in Cochrane reviews, we have small number of studies. And in order to better calculate a confidence interval, we recommend calculating a confidence interval for at least 5 studies in the meta-analysis. Now, similarly, in this example, we have 11 studies, which is almost double of what we had in the previous example. And in this empirical example, with all these studies, which is not mostly not the case in Cochrane reviews, if we also estimate heterogeneity using the 2 approaches, the Dersimone and Laird and restricted maximum likelihood, we can see that the estimates are closer to each other now. The impact now on the confidence interval for the summary effect is small because of this small difference between the 2 estimators. And we can see that the 95% confidence interval in the summary effect spans from considerably reducing the risk of mortality up to a trivial risk decrease or equivalent risk between the 2 groups. Now, as the number of studies increases in the meta-analysis, we expect that the 2 approaches, the Dersimone and Laird and restricted maximum likelihood, to perform comparably. And as the number of studies increases, both simulation studies have shown that the performance of the 2 approaches improves. But even in such situations where we have a lot of studies, simulations have shown that RevMan provides even more accurate estimates than Dersimone and Laird. And as I said earlier, a confidence interval for the tau square would be helpful to infer on the precision of heterogeneity. Now, another important finding from simulations, and as we can see in this example, where we have 5 studies, is that the de Simone and Laird frequently estimates tau equal to 0, and therefore the I-squared again will be 0%. Here in this example, on average, the studies have pretty similar odds ratios, but taking a closer look at the studies, and maybe at studies A and E, we can see that they have a small overlap in their confidence intervals. And also having a look at study B, which is the smallest study in this meta-analysis, we can see that this study has a very large, wide confidence interval, suggesting even that the treatment may not work. Now, based on the restricted maximum likelihood estimator, we estimate this tau positively equal to 0.02. So the I-squared also increases from 0% to 7%. So we can see that when we have cases with de Simone and Laird equal to 0, then restricted maximum likelihood might find this small heterogeneity compared to DL. But overall, the difference in the two estimators here is not important, and therefore we don't see a big difference between the confidence intervals. And again, we have poor estimation of tau. We have only 5 studies, so the estimation is imprecise, I would say. So a confidence interval would be helpful in order to infer on heterogeneity. As pointed earlier, and when the number of studies increases, de Simone and Laird tends to agree with the restricted maximum likelihood, and especially in the case where heterogeneity is small. So simulations have shown that de Simone and Laird performs well when heterogeneity is small or close to 0, and when there is a large number of studies. So here in this example, we actually have a lot of studies. We have 12 studies for aversive smoking, for smoking cessation, and the estimated tau with the 2 methods is equal to 0, which actually is the fixed effect approach, is the fixed effect model. So here the results would not be affected using any of the 2 estimators, since both actually reduce to the fixed effect model. But always when there is a sufficient number of studies in the meta-analysis, we can calculate a confidence interval to infer on the precision of tau. Overall, we expect in reviews with large number of studies, more than 10 studies, that the results are comparable between the 2 methods. So as the number of studies increases, then we expect that the 2 estimators will be in agreement. Now, in case of rare events, both de Simone and Laird and restricted maximum likelihood tend to underestimate heterogeneity. So here, for example, we have 18 studies. However, only 10 studies contribute to the meta-analysis. We have 8 studies that had 0 events in both arms. And the studies compared long-acting injectable antipsychotics versus placebo for all-cause mortality. And we can see here that we have approximately, I think, 6 events that were reported in this drug arm out of the total 2,000 participants. And then in the placebo arm, we have 7 events out of the approximately 4,000 participants. So this shows us that we have rare events in this meta-analysis. So estimating heterogeneity in rare events is a very challenging task due to the wide confidence intervals across the studies, due to the sparsity of the data. And as you can see, with both estimators, heterogeneity has been estimated equal to 0. So ideally, we would like to calculate, in these cases, a confidence interval to see the imprecision of the uncertainty around the tau square. However, in this case, we were not able to calculate a valid confidence interval. This led us to a null empty set where the lower and upper bounds of the confidence intervals fell below 0. And that's why I would not present this here. But this is a rare case that happens in when we try to calculate the confidence interval for tau square. So overall, we should consider that in meta-analysis with few studies, fewer than 10 studies, and meta-analysis with small study sizes and rare events, estimation of heterogeneity can be imprecise. Now, for very few studies, both the Simon and Laird and restricted maximum likelihood tend to underestimate heterogeneity, such as in these examples where we have 3 studies here and 2 studies here. So we can see that both actually methods give comparable results, but we have wide confidence intervals. However, a restricted maximum likelihood in most cases performs best, such as in this example where we have only 3 studies and the confidence interval, again, we can see that it is wide, but REML is higher than the Simon and Laird. And according to simulation findings, again, REML performs best, particularly when heterogeneity is high in the meta-analysis, such as in this example again, where, again, restricted maximum likelihood is higher than the Simon and Laird. So overall, we saw several cases empirically, which actually support simulation findings, despite we don't know the true heterogeneity in these cases, but we can see that there is a tendency of the Simon and Laird to give smaller heterogeneity values compared to the restricted maximum likelihood in most of the cases. Now, at the second part of this webinar, we will discuss about the inference on the summary effect size. And let's see in particular, the decisions that we made for calculating the confidence interval for the summary mean effect. And these are based on the estimated tau in the first step and the number of studies that is represented by K here. So this is again based on simulation findings and the properties of the Hartung-Knapp-Sitting-Jonkman and the wall-type approaches. Now, overall, in case of heterogeneity that is positive, is above 0, and in case the number of studies is equal or above 3 in the meta-analysis, we recommend to use the Hartung-Knapp-Sitting-Jonkman method in RevMan. But when heterogeneity is equal to 0, and when we have the number of studies in the meta-analysis equal to 2, then we recommend to use the wall-type method. Currently, regarding this aspect, there is some decision to be made in the case of 2 studies, given that we initially started by suggesting to present both approaches, but now we move towards to the presentation of the wall-type only approach, and we will explain in the next few slides the reasons behind this decision. Okay, so going back to our previous example with the 5 studies, we calculated both wall-type and Hartung-Knapp-Sitting-Jonkman. And as you can see, the Hartung-Knapp-Sitting-Jonkman method gives wider confidence intervals. So overall, and according to simulation studies, the performance of the wall-type method depends on the number of studies that we have in the meta-analysis, the estimator of heterogeneity that we use, and the magnitude of heterogeneity. In case of few studies, like in this example, the wall-type confidence intervals are very narrow, and that's why usually the wall-type method gives statistically significant results more often compared to the Hartung-Knapp-Sitting-Jonkman. However, this happens because it is associated with inadequate properties. It has lower coverage compared to the Hartung-Knapp-Sitting-Jonkman method. Now, let's take a look at the formulas for calculating the 2 confidence intervals. So the confidence interval of the wall-type method uses the normal distribution and the usual 1.96. But the Hartung-Knapp-Sitting-Jonkman method uses a t-distribution, and the t-distribution has heavier tails, and we expect that it will give us wider confidence intervals. So the quantile of the t-distribution is larger or equal to the quantile of the standard normal distribution. And let's take a look at this example that we saw earlier for dysmenorrhea and acupuncture versus medication. Here, as we said earlier, we have 6 studies. The mean difference is the effect size, and the estimated heterogeneity is equal to 2.8 using the restricted maximum likelihood. Now, comparing the 2 approaches, the Hartung-Knapp-Sitting-Jonkman and the wall-type method, we can see again that the Hartung-Knapp-Sitting-Jonkman method gives wider confidence interval. And this is in accordance to simulation findings. It produces wider confidence intervals, but it has higher coverage than the wall-type method. It has a better performing profile. It is not influenced by the magnitude or estimator for heterogeneity, as long as heterogeneity is positive. So here, the width of the Hartung-Knapp-Sitting-Jonkman method is larger because of two main reasons. So one is because of the t-distribution, as we said earlier, but also because of the differences in the two variances calculated for the summary effect. So the Hartung-Knapp-Sitting-Jonkman variance incorporates an extra quantity, the small sample adjustment, that accounts for heterogeneity. And the Hartung-Knapp-Sitting-Jonkman method, variance is a weighted extension of the wall-type variance. So when the heterogeneity is above 0, the variance of the Hartung-Knapp-Sitting-Jonkman will be larger than the variance of the wall-type method. Now, in our example, the two confidence intervals do not substantially differ, but still the Hartung-Knapp is wider. Overall simulations have shown that the Hartung-Knapp-Sitting-Jonkman method has one of the best performance profiles. It has high coverage to detect the true value, irrespective of the estimator for heterogeneity, and that's the added bonus compared to the wall-type method. So the choice of the estimator for heterogeneity, let's say, becomes less important. But we need to be careful when heterogeneity is equal to 0. And we're going to see this in the following example. So here, in this example, we have 6 studies in the meta-analysis assessing alcohol-related problems. And when we applied both wall-type and Hartung-Knapp-Sitting-Jonkman methods, we saw that the wall-type method was wider than the Hartung-Knapp-Sitting-Jonkman. And this is actually the opposite of what we have seen and we have been discussing up to now. So the Hartung-Knapp method is not conservative anymore compared to the wall-type. Now, taking a look at the estimated heterogeneity, we can see that heterogeneity is equal to 0. And in these cases, simulations have shown that the Hartung-Knapp method is suboptimal compared to the wall-type when in the absence of heterogeneity. So the Hartung-Knapp method results in shorter confidence intervals than the wall-type method in these cases, but also it has lower coverage compared to the wall-type in the case of tau square equal to 0. The most concerning part is that the Hartung-Knapp-Sitting-Jonkman method confidence interval becomes shorter even from the fixed effect model, which is the strongest assumption, if we can say that, about homogeneity in the data. We assume that there is no heterogeneity. So in the context of random effects meta-analysis, we expect that a confidence interval for the summary effect is always at least as wide as the confidence interval from the fixed effect. Now, with the wall-type method, we can ensure this, that it is equivalent to the fixed effect model when tau is equal to 0. But the Hartung-Knapp method does not ensure this. And again, having a look at their formulas and the variances for the mean effect, we can see that the variance for the Hartung-Knapp-Sitting-Jonkman is smaller compared to the wall-type variance. And that's because of the tau square that is equal to 0. Now, similarly, in this example, we have estimated a tau square equal to 0. And again, in the absence of heterogeneity, the Hartung-Knapp gives a shorter confidence interval compared to the wall-type. And as we can see, that happens irrespective of the number of studies that we have in the data or the type of data that we have in the meta-analysis. So the Hartung-Knapp-Sitting-Jonkman method is not always conservative compared to the common effect meta-analysis. And considering that also the coverage is not acceptable in this case, according to simulation studies, we suggest that the wall-type method be used, which directly avoids this issue. So the Hartley-Knapp should not be used when we have the tau squared equal to 0, and we recommend to use the more conservative confidence interval. Now let's see a few more interesting cases, and when the number of studies is below 5. Now, in these forest plots, there are 4 and 3 studies in the meta-analysis respectively. And as you can see, we have positive tau squares, so they are above 0 in both cases. Now, in the first forest plot, both the wall type and the Hartung-Knapp-Jonkman methods give summary effect below 1 on the odds ratio scale. And this is in accordance to the studies as well. As mentioned before, the Hartung-Knapp-Jonkman is wider than the wall type method. Now, in the second forest plot, there are 3 studies with odds ratios and confidence intervals above 1, again, on the odds ratio scale. The wall type method gives a confidence interval for the summary effect, which is also above 1. But if we see at the Hartung-Knapp-Jonkman confidence interval, this extends to the confidence interval extends to an odds ratio below 1. And that's because in the case of small number of studies in the meta-analysis, the small number of studies increases the t statistic inflation. So we get wider confidence intervals. And potentially in this case also because we have a tau square which is large, and this is also accounted in the variance of the summary effect. But overall, we have noticed that empirically, in the case of 3 studies, and particularly in the case of 2 studies, the confidence interval for the Hartung-Knapp-Jonkman method becomes very wide. Simulations have shown that in the case of 3 studies, the Hartung-Knapp has higher coverage compared to the wall type method. So one would think potentially that this is how it should be. We should have wide confidence intervals because with only, let's say, 3 studies, here our inference can only be imprecise, obtained from the random effects. But then let's have a look at this example where we have only 2 studies. And the Hartung-Knapp-Jonkman method here becomes extremely wide in this case. So we get overly conservative confidence intervals. And usually, like in this case, non-informative results when we have only 2 studies in the meta-analysis. Considering also the simulation findings that the Hartung-Knapp-Jonkman has very low power, in this case compared to the wall type, we are recommending actually in these cases to use the wall type method. But of course, the selection between the 2 methods is a matter of power and coverage or type 1 error to keep a balance between the 2. Moving on to the case of rare events and using the previous example where heterogeneity is equal to 0, we would prefer to avoid the Hartung-Knapp-Jonkman method in this case. And that's because simulations have shown that the Hartung-Knapp-Jonkman is suboptimal compared to the wall type in meta-analysis of rare events. And that's possibly because usually we estimate heterogeneity equal to 0. And because of this, the Hartung-Knapp is likely to be shorter compared to the wall type. And again, this would be avoided if we selected the wall type method. Now, in the case of many studies in the meta-analysis, like the one that we have in this empirical example, where we have 18 studies, the wall type method performs well when a large number of studies is included in the meta-analysis. There are no major differences between the 2 approaches, but we need to remember that the wall type method also depends on the heterogeneity magnitude and the heterogeneity estimator. Therefore, even in this case, we would prefer the Hartung-Knapp method, which is insensitive to the magnitude of heterogeneity. So I will stop here and I will pass it over to Jo to continue with the prediction intervals. And I'll stop sharing my screen.
Okay, thank you very much, Arji. So I'm going to move on to just talk about prediction intervals, and I'm going to use this example, this slide come from Julian Higgins, to juxtapose two meta-analyses. In this first case, what you can see here is that we've got a lot of consistency in the effect estimates when you just kind of eyeball the point estimates and their confidence intervals. And here there's a summary effect of 1.64. Now, if I put up this particular meta-analysis here, I'm sure you'll all agree that we've got a lot of heterogeneity. There's a lot of dispersion in those point estimates and confidence intervals. But in fact, what we get here is exactly the same pooled effect and confidence interval and p-value. And so just by presenting the summary effect, we're missing this really key important information, which is about the dispersion of effects. And here, just you can see these highlighted green and red showing some of the treatment effects are favouring, some of the effect estimates favour treatment and some favour are harmful, show that the treatment's harmful. So we need to better be able to incorporate this additional piece of information, which has not really been the focus of many systematic reviews historically. So this is where prediction intervals come in, and this is a new quantity that, or a new statistic or interval that has been added into RevMan. It's an optional thing that can be done, and we would recommend that it's only done when you have a particular number of studies, at least 5. At a minimum, very minimum. And I'm going to talk through on the next slides the particular options about how the prediction intervals actually will be implemented in RevMan. So as Archie's already introduced, when fitting a random effects meta-analysis, we often assume that the underlying intervention effects are normally distributed around a mean, and we can calculate this confidence interval, which tells us about the uncertainty and our estimate of that mean. What the prediction interval does, though, is we have this quantity tau that Archie's talked at length about, which is just the standard deviation of the underlying treatment effects. So we can use that piece of information. If we assume that the intervention effects are normally distributed, then what we would know is that 95% of the true treatment effects would fall within the interval of the mean, plus or minus 1.96 times that standard deviation. And so what this prediction interval tells us is it's the interval within which we would expect that the effect of a future study would lie, or perhaps a more understandable interpretation of it is that it's a summary of the spread of the underlying effects in the studies included in the meta-analysis. And so let's look at some examples to explain this. Oh, well, before I get onto the examples, just to say that that this is an approximation to how we calculate the prediction interval here. But in practice, we actually have to estimate both the summary effect, the meta-analysis effect, and the tau, the standard deviation. And so we need to account for that when we actually calculate our prediction interval. So the method we use to account for that is that instead of just multiplying by the quantity, the square root of tau squared, we also have to add in the fact that we have some uncertainty in estimating our summary mean. This M here is the multiplier, and this is dependent on the confidence interval method that you will use. So if you've used the wild type confidence interval, then this M will be a Z quantile for the prediction interval. If you use the Hartung-Knapp-Jonkman confidence interval method, then that multiplier here would be the T distribution quantile. And this particular choice of multiplier means that in the absence of heterogeneity, the observed confidence interval and prediction interval will be identical, which is what we want. So here's an example of a prediction interval. So you can see we've got a range of effect estimates and confidence intervals, and our metric here is a hazard ratio. And we might be interested in 2 questions. So does the treatment event reduce the risk of having an event? And does the effect size vary across the studies? Now, if we look at these effects and confidence intervals, what you can immediately see is that we've got this point estimate and confidence interval here, which is showing that the intervention looks to be extremely effective, whereas up here, the intervention is looking harmful. And so we've got a range of intervention effects showing quite different things. In terms of the kind of some technical properties, to actually calculate a prediction interval when we have ratio measures like odds ratios, hazard ratios, and risk ratios, we first of all need to log transform them. So that's what's done here. I should say overall our summary estimate is 0.6. So there's a 24% reduction in the hazard for those who are receiving treatment. But obviously that confidence interval includes the null effect there of 1. When we calculate our prediction interval, we do this on the log scale. So this 0.4 here squared is the tau squared value, and this 0.14 here is the variance of the summary effect. We calculate our prediction interval on the log scale, and we back transform that. And where our back transformation gives us the range of underlying true intervention effects. And what we can see is that that's ranging from 0.33 to 1.75. So in any particular study, we could see that the treatment could be very harmful to actually, very beneficial to very harmful. So it provides us this extra piece of information that we don't get just from looking at the summary effect and its confidence interval. So here, the true summary log odds ratio probably falls in the interval of 0.58 to 1.00. That's how we would interpret our confidence interval when we interpret the prediction interval, which is telling us about the dispersion of the effects. The true log hazard ratio for any single study will probably fall in the range of minus 1.1 to 0.56. And when we back transform that to hazard ratios, as I said before, that ranges from 0.33 to 1.75. In the previous calculation, we used the the normal distribution quantile. If we use the t distribution quantile, you can see that we get a slightly wider confidence interval, prediction interval, I should say. And so here, the difference between the two is not major, and that's because we have quite a number of studies in this meta-analysis. But they will be quite different if you've got a smaller number of studies. And let's just look at an overall example, looking at the recommended methods. This is a meta-analysis looking at the effect of quality improvement strategies for the coordination of care on hospital admissions. Ratios, what we have is our metric here is odds ratios, and odds ratios less than 1 indicate decreased odds of admission to hospital. So when we look here, we can see that there looks to be quite a lot of variation in the treatment effects, just looking at the forest plot. But when we calculate an odds ratio, our summary effect here, we get a value of 0.72. So there's a 28% reduction in the odds of hospital admission for those hospitals that are receiving the quality improvement strategies compared with those that aren't. And what we can see is our confidence interval rules out the null value. We might debate as to whether if the odds ratio was 0.97, whether this would be a truly important difference. But just interpreting this result, many people would probably come to the conclusion that it looks like quality improvement strategies are effective, but that ignores the dispersion of the intervention effects. So we can see here we've got a Q statistic, which is in this p-value here is very small. So this is from the test looking to see whether there's evidence of heterogeneity. So that gives us an indication that that is the case. Our I-squared statistic, which is telling us about the percentage of variation in the effects beyond chance, is 63%. And our estimate of heterogeneity variance is 0.154. But that in itself is not particularly easy to interpret. So if we use that to calculate a prediction interval, what we can then very easily see is that the summary of the underlying intervention effects ranges from an odds ratio of 0.3 to 1.73. So that in any particular scenario or hospital setting, again, this intervention could be very beneficial or potentially very harmful. And so this is another key piece of information we need to interpret when fitting a random effects model. Okay, what to write in the protocol? Well, I've just pulled out some of the kind of essential elements from the PRISMA statement. And essentially what we're suggesting is that the particular meta-analysis model needs to be reported along with the method and any method used to identify or quantify statistical heterogeneity, which includes prediction intervals there. And also, we're asking for people to report the between study heterogeneity variance estimator. So in the case of Cochrane reviews, this will be Dersimony-led, or the restricted maximum likelihood estimator, and also the method used to calculate the confidence interval for the summary effect. And in the case of what the recommendations that we're putting forward, we would also suggest that you would write the scenarios in which you would pick the particular confidence interval method. Okay, so in terms of what's next, in December, we are coming back where we will actually show how these methods have been implemented in RevMan. So we'll have a demonstration of that. And I think now we're going to, I'll thank you for attending, and we would welcome questions.